Hello everyone, my name is Ranjit, Application Engineer with Mirabilis Design. I would like to welcome you all for today's training session. Today we'll be looking at scheduling analysis for real-time applications, and the session is going to be a combination of presentation and demonstration. I'll be walking through some of the concepts of schedulers and the kind of resources that we provide in VisualSim Architect to model your software architecture, and also to model your schedulers and the kind of scheduling algorithms that we provide as part of the tool itself. So I would like to recommend you to, if you have VisualSim installed on your machine, I would recommend you to start up the tool and have it ready. You could try to use VisualSim as I go along through this presentation, and also when I start using models to construct complex applications and things like that. And today I'll be going over a few concepts. I'll be taking up very simple scheduling models. And also I'll be looking at avionics applications. For example, I'll be considering Ring 653 itself. And also I'll be looking at uh, automotive applications as well. So how exactly one can inject faults to the time space or the kind of faults related to software part of the system, or it could be memory faults and things like that. And I'll be walking through a couple of demo examples as well in addition to constructing some models. And I hope you enjoy this session. So before getting started with today's session, uh, here's some logistics details. There is a control panel on your desktop right-hand side. You can post in your questions in the chat window, and I'll be taking up these questions in between and also at the end of the session as well. And also we have people in standby, they'll be answering your questions as well. So here's a quick outline to today's training session. I'll be just giving an overview about what exactly we did in our previous sessions, and talking about what exactly is a software task and how it can be defined. And we'll be looking at I'll not be going in details about a distribution across multi-core architecture, as it is a broader concept. We will be actually taking up this as a separate training session in the upcoming days. And I'll be walking you through the modeling resources that are available with VisualSim to be able to model your software applications and also the hardware architecture to be able to understand what is the performance that you're getting, whether the tasks are executing in the given timing deadline time, or are they taking more time than expected and things like that. And also I'll be constructing few example systems as well to give you a feel about how quickly you can construct the models. And I may not really go into too much details about it, but if you have any questions about any specific aspects, you can post in your questions. I can actually go over those concepts as well. So in our previous sessions, what we did was we actually went through basics of VisualSim Architect itself, how exactly one can construct a simulation model, and what are the kind of modeling framework, or what are the resources that are available. And also we talked about how exactly one can select a library block to model a software behavior, or it could be in hardware architecture and things like that. And also we went through how exactly one can utilize a parameter to configure a system architecture, and how effectively they can run through multiple variations of the system architecture to make sure a particular architecture is going to meet the requirements or not. And also we went through how exactly one can model a performance model of a complete system architecture. It could be a complete avionics platform, or it could be a complete SoC board, or things like that. We looked at what are the different types of analysis, including how can I capture the utilizations or latencies or throughput and things like that. And if you have not attended our previous sessions, I would recommend you to go to our YouTube channel and uh, watch through these training sessions. So going over to today's session about software tasks and scheduling analysis uh, of real-time applications. A software task is nothing but it is a kind of unit of execution in a software itself or an application software. So if you actually break down your application software into multiple pieces that you could be interested in running in multiple hardware resources you may have in your hardware architecture, you can actually consider that as a task itself. And every time a particular task is being released, it is actually kind of go through a number of instruction processing or execution on the target platform architecture itself. And these also could trigger a subsequent tasks, or it could actually a kind of completion of a particular activity itself. So if you look at the state of a software tasks, uh, if we consider the complete life cycle of a particular software task itself, it will essentially have 4 different states. You will actually have your inactive states whenever it is not being triggered or something like that, and then you have your ready state and waiting state or executing states. So these are the different states that you will actually uh, go by selecting a different scheduling algorithm. For example, if you have a preemptive scheduling algorithm, then you would actually have, if there are any kind of higher priority tasks that are going to come in, you will actually have to preempt the tasks that are actually having lowest priority and take up the highest one. So you will actually have to place your preempted task in a preemptive queue or something like that and take up that particular task later in the uh, simulation time to be able to complete that activity itself. So these kind of preemptive based scheduling may cause sometimes uh, may not able to meet the timing deadline what you are expected, or maybe you may really need those preemptive tasks to make sure that the functionality of the complete application is going to meet all your requirements and things like that. So these software tasks, if they are not defined correctly or if they are not mapped onto the hardware architecture correctly, and if you have not selected the scheduling algorithm that is going to meet all your requirements, you may actually have certain set of problems. If everything is perfectly fine and if you have so many tasks that are running on multi-core processing platform or things like that, the execution and functionality may completely maybe very well. But if there are any kind of problems, for example, if you compare these two graphs over here, in the top one, we actually have two ECUs in an automotive platform on which we are running multiple workloads and use cases. And we can see here that all the executions are kind of symmetrical. But if you look at the second plot over here with a different set of workload scenarios, we actually see here that the execution of or the activity of the processors or the ECUs are completely different over here. So this could be kind of problems related to your hardware architecture itself, or it could be the way how you're defined your software behavior flow as well. And also if you will actually have to consider the scenarios such as uh, your resources may not be ready or may not be available, or there could be kind of dependencies as well. For example, you may actually have dependencies in terms of tasks. Maybe if you have 4 or 5 different tasks that are going to define a particular applications. If you are expecting task 1 to kind of precedence the next task, for example, task 2 or something like that, if task 1 takes more time than expected, your second task may actually take more time now. So these kind of dependencies may actually cause a lot of problems as well, and you will have to identify and you will have to address these dependencies problems and not meeting the timing deadlines and all that. You will have to identify at the early stages itself. And also you may have scenarios such as you may have shared resources as well. So if you are actually having multiple tasks that are running and there is a kind of shared resource that you have, or maybe a kind of external memory or something like that, if that particular memory location is locked by another task, you will actually have to wait for that particular the previous task to release that particular memory location, and then only you can take up that or access that particular data. So these kind of problems are the kind of dependencies will actually have impact on the execution of the task on the target platform itself. And you will have to identify the kind of impact of these distributions on a single core or a multi-core architecture to make sure if the task deadline times are met, or if they're taking more time, what is going to be the impact of that extended time, or kind of task deadline exceeding on the total performance of the system architecture itself. Okay, so those are the kind of problems that you could expect, and you will have to identify those problems as early as possible in the design process before writing your application software or before having your architecture ready with you. So if you consider a kind of RING 653 or a multi-processing, because the reason is that I'm talking about this particular slide over here is that uh, the systems are actually going, as you know, systems are going with multi-core architecture, and we are no longer uh, with a single core architecture in most of the applications, I would say. And if we consider RING 653 itself over here, in this case we have two partitions over here, and we have multiple processes or tasks or activities that are running on each partitions itself. And in this case we have considered, or we have dedicated each processor core into each partitions itself. And it could be other way around as well. If you have a single core architecture, you will actually have multiple partitions in a specific core itself. And the major reason for doing all these partitions is that you will actually have a kind of assurance in terms of execution of the task itself. And also you will have to, or you can make sure that, or you can secure that if a particular partition goes down, or if a particular task is unable to finish its processing in a given timing deadline, the other tasks will not get affected because of it. So these kind of problems you can actually address with this virtual machines, or having multiple partitions or things like that. And these are the kind of, these also provide or kind of poses challenges in terms of meeting timing deadlines as well. For example, in this case, if you notice over here, we have actually an external memory over here, but if the processes, or if the tasks are trying to access the same data or same data location in the memory, so that may actually cause dependency problems, or you may actually have to wait for a certain time period and things like that as well. So at early architecture exploration, or to be able to understand what is going to be the impact of these shared resources and dependencies of tasks on the end-to-end system latency or task processing latencies is going to be very important as well. Okay, and I'm going to go over a example as well. So in order to identify, in order to fix these kind of scheduling problems, we actually provide varieties of ways to do it. So one thing is that with early architecture explorations, or with by enabling the user to construct simulation models of your software architecture as well as hardware architecture, we enable you to make changes in terms of requirements as well. For example, if you have provided an execution time for a particular task of about 10 milliseconds, and if you're not able to finish that within 10 milliseconds, you can actually try to extend it. Whereas if any other task which is actually not taking that much time, or what you have provided, you can reduce those periods as well. And also you can go with a highest or faster CPUs as well, or you can reduce the blocking factors itself in your system. And also you can go with modified task mapping mechanisms as well. For example, if you have multi-core processing platform, or for example, if you have two processors, and the way how you are defining or mapping your software applications onto the target platform, you can change the way in which you're mapping and the kind of dependencies that are there right now, and try to understand how exactly or how efficiently you can eliminate those dependency related problems and things like that as well. So essentially we actually enable you to model your software behavior as well, and your scheduling algorithms, and your allocation of the resources itself. It could be allocation of semaphores, or it could be timers, or it could be memory related stuffs and all those stuff, you can actually decide and you can allocate with VisualSim, and then you can actually go with uh, the architecture which is going to meet your requirements at the end of the simulation or end of the exercise itself. So with regards to modeling resources that are available with VisualSim, if we actually split up our system model into three parts, I would say. One is that your software modeling itself. We actually provide libraries such as expression list, script blocks, and mappers, and also we have FSM as well, finite state machines, which actually enable you to model your software behavior sequences. And in terms of hardware modeling libraries, we actually provide hardware accurate processing libraries or processors all the way from ARM, PowerPC, Intel, and things like that. And also we have statistical processing resources such as system resources, which actually enable you to model your processor, bus, memories, or caches, and things like that. And also we have libraries such as queues and servers, and also we have quantity-based resources as well, which actually enable you to model your resource allocations such as semaphores and things like that as well. With regards to task scheduler or the scheduling portion itself, system resource itself includes a scheduler in it. By default, we provide first come first serve and first come first serve plus preemption, and also we provide round robin scheduling algorithms. But also we enable you to define your own scheduling algorithms as well. And in addition to that, library blocks such as queues and servers and database blocks, FSMs and expression list will actually enable you to model your scheduler portions as well. And actually, I'm going to utilize all these library blocks in today's session, and I'm going to show you how exactly each of these different components or part of the systems can be constructed with VisualSim itself. And also, if you have any kind of pre-built models in MATLAB or Simulink, or C or C++, you can actually bring in those models into VisualSim as well as is. So you don't really have to create any additional models with that. And also, you as a software engineer or as a systems engineer, you might be very much familiar with SysML technology or methodology itself. So SysML to VisualSim, we actually provide a kind of direct translation, but right now we are not doing any kind of automated translation, but we actually provide one-to-one mapping to the blocks that are available in SysML to VisualSim itself. For example, we have library blocks for defining your hardware architectures itself, or defining the use cases or workload scenarios, and defining an behavioral sequence for an application itself, or it could be mapping of your behavior applications under the target platform itself, and to be able to have your various analysis tools and parameters as well. So we actually provide a whole variety of different library blocks that are quite similar to SysML approach as well. So that way you can, if you have any SysML models, you can actually quickly construct VisualSim models by referring to your SysML model itself. Okay, so in terms of fault tolerance, because fault tolerance is one of the crucial factor that one must consider. For example, if you have any kind of modified schedule table, let us say you have a major frame duration of about 16 milliseconds, but your minor frame durations are actually having about 20 milliseconds of multiple time slots or virtual machine slots. You will actually have, if a particular virtual machine or particular slot is taking more than expected time period, so that particular task may be actually considered as a failure itself, as you may not able to pass it on to the next partitions if it is a kind of hard real-time requirement or things like that, or security related stuff. You can capture those kind of problems and to be able to consider or model scenarios to avoid those scenarios as well. And in addition to that, a software part of the system, we actually provide or enable you to introduce various a different type of failure scenarios into system, and to be able to have a fault tolerant system. For example, if a network link between one node to another node goes down, what exactly uh, going to be the impact of that, and what one can consider to be able to avoid a complete failure of the system platform itself. And also enabling you to kind of deadline failures, or it could be a kind of slow failures of a power systems or a network overload related stuff. You can inject various types of fault scenarios into VisualSim itself. So at this point, I would like to quickly show you a VisualSim model to give you a feel about how exactly those models would look like. And here is a model of an AutoSAR system environment in which we have multiple sensors, the network itself we have modeled over here. And over here we have defined the ECU hardware, which actually includes two CPU cores over here, or ECUs. And also we have various different set of software related stuff. Consider in this case we have considered we don't really have the application software ready, but instead what we have done over here is we have provided a task table, which actually allows you to define your various different task details. Um, for example, if I look at this particular task table, I've defined a different set of tasks over here, and also I have provided some dependencies as well. So if I have to execute a particular task and I have these different set of dependencies defined in my model, and also I have defined where exactly these tasks are gonna run on my platform as well. In case of multi-core processor platforms, you can define those scenarios as well. In addition to that, what you can do is you can define your deadline or schedule time as well. So at what time a particular task must execute, and what are going to be the dependencies between those tasks as well. And if you look at the other attributes, for example, if you have a particular task, what is going to be the maximum or the kind of deadlines between those different tasks as well, and what would be the kind of maximum time a particular task can spend up to. Okay, so in this case what I'm going to do at this point is I'm going to run the model, and here what we have done over here is we are actually running multiple runnables on the multiple ECU or two CPU boards here, and I'm looking at the execution of ECUs itself or tasks on the ECUs itself. And also I'm looking at which are the different tasks that are actually not meeting the timing deadline, and they're going above the tasks that are meeting the timing deadlines as well. Okay, and also we are looking at how many tasks that are actually being waiting for processing, and how many are running and things like that. If you notice over here, we're actually looking at initially we actually had a lot of tasks that are actually waiting, but later on it started dropping off. Also, in addition to that, here we are looking at utilization of various resources as well. So we are looking at processing resource utilizations as well. So this actually provides you a kind of complete end-to-end analysis report to be able to understand how much time each task is taking to execute on a target processing platform, and what is my utilization statistics for my hardware architectural resources as well. So in this model, we also have captured power consumption of my complete system as well. So this actually enables you to kind of consider the impact of software task execution on the complete system power consumption itself. So if you notice over here, we're actually consuming about 1.6 kilowatt of power of considering the complete system platform itself. Okay, so what I'm going to do at this point is I'm going to kind of inject a fault, so which we have actually modeled as it as a parameter, in which we actually have at the bottom we have error scenarios that are actually related to runnable executions, and also we have we are introducing memory faults as well. For example, accessing the wrong memory locations, or writing the wrong data to a particular memory locations while you're running through the simulation. So if I go ahead and run the model with fault enabled, or after enabling the fault, so if you see over here, my latency across my platform is actually quite high right now. And also what I can see over here on the execution of tasks on the ECUs, you can see here till 1.2 everything was actually going very well. But after that EC1 started degrading, or you're not EC1 itself is not receiving the tasks, or maybe the data is being corrupted. So these kind of problems are actually you can capture and you can address with VisualSim itself. Okay, so with the analysis reports that we actually provide, or that you actually generate out of VisualSim Architect, you can conduct various design decisions. It could be selection of your hardware architecture elements, or it could be certification related stuff itself, or it could be measurement and management of power consumption itself. If the power consumption of your system platform is more than what you're expecting because of the way how you're distributing your tasks on your processing platform, you can actually try to find a way to reduce the power consumption itself. Maybe you can introduce some sleep states whenever you're not running anything on the hardware platform, or you can actually map your applications onto multiple processing resources in a specific manner. And also you can try to understand or identify the scheduling algorithms, or how exactly the tasks must be executed on, whether they have to execute in a specific order, or how exactly I need to allocate my resources for my execution itself. If I have a if I have about 1 kilobyte of memory, so what is going to be the kind of maximum memory consumption of by my system resources itself, and whether do I need to allocate more memory for running my applications and things like that, you can uh, identify as well. Okay. So in order to define a software behavior flow, if we look at any software behavior, or a particular task behavior, you can actually see something like this. You would actually generate a particular task, and that particular task may actually have certain attributes. For example, what is the size of the data that you're expecting, or you're writing into a memory or something like that, and what is the rate at which you're generating those tasks, and what is the priority associated with that, and maybe some other factors as well. And then you would actually do a kind of memory read operation, and then you do get resources, and then you would do a kind of task processing on the target processing platform, whether it could be on a single processor or multiprocessor. And then once your processing is over, you will actually write back the data to the memory location. So if you look at VisualSim methodology, or with regards to defining the software behavior flow, we actually provide exactly the same way how it is being done. We actually provide a traffic generator block to define your or generate your task itself. And for performing your memory read and write operations, we actually have the DMA controller. And then to be able to get the resources or allocate resources to make sure that the task is going to have sufficient memory space to make sure that to make sure a successful completion of that particular software task execution, we provide a resource allocation block for that. And to be able to map the applications or tasks onto the target platform, we provide mappers and system resources itself. So mapper is a block, we call it as a behavior piece of it, which actually allows us to map a particular task onto a specific hardware element in the target platform. It could be a processor, it could be an FPGA, or it could be a custom ASIC board and things like that. Whereas system resource actually enable you to define your statistical processor or any other dedicated accelerators or things like that itself. For defining or to be able to model a DMA controller, a DMA store operation, we actually have a DMA controller to write the data back into the memory location. So this is how exactly a software behavior flow would look like if we actually go with flow diagram based software behavior flow definitions. in addition to that, we also have an ability to model using FSM as well, or finite state machine as well. I'm going to show you that in a little bit. So what I'm going to do at this point is I'm going to just close this model. So as I talked about scheduling algorithms or execution of tasks on the target platform, at this point what I'm going to do is I'm going to create a simple system with a first come first serve scheduling algorithm, and I'm going to create 3 different tasks, and tasks are going to have multiple priorities. For example, one task can have lowest priority and the other can have highest priority, and also each task are going to take about 3 milliseconds of simulation time. I'm going to model this particular scenario using VisualSim blocks, and the candidates for modeling such a system would be system resource block, which actually helps me to define a resource, considering it as a CPU or something like that. And to be able to define tasks, we actually have library blocks such as traffic generators. And to be able to map the generated tasks onto a system resource or a CPU, we are going to use a mapper block. So we actually have gone through this scenario in our earlier session, but I would like to go over that once again to make sure that you can follow that easily. So I have opened up a new block diagram editor. First thing that we need to do is we need to bring in a digital simulator. So I just double clicked on the digital simulator block, and I'm going to define the simulation time. I'm going to set this to 10 seconds. And then what I'm going to have is I'm going to instantiate a system resource block, and this is going to, or this represents my CPU or a processor itself. In this case, we are not considering any detailed processing model because we are focusing more on the software or task or definitions. So what I'm going to do is I'm going to set this to 500 megahertz, and it is going to take a relative time, which means it acts as a time-based delay. And the scheduler type that I'm going to set this to as first come first serve. In addition to that, we have first come first serve plus preemption and round robin as well. And also you can utilize your own user defined scheduling algorithms as well. And I'm going to set this to first come first serve. I have instantiated traffic generator block to define my task definitions for my task 1. And I'm going to instantiate a mapper block, which actually helps me to map the generated tasks onto the CPU block over here. And this model is going to be very simple. And I'm going to generate this at 0 simulation time. And after that, it is going to generate for every, I'm going to set this to single event. So let's keep it very simple. And I'm going to define the parent scheduler or parent resource as CPU. And I'm going to set this as task number 1, and priority I'm going to set this as 1, and task time I'm going to set this as 3.0. So what it means is it is going to spend about 3 seconds of time on the target processor over here. Okay, I'm going to copy and paste to create another instance. So I'm going to start this at 2 seconds. Earlier, the first one was actually starting at 2 seconds. I'm going to start at 2 seconds over here. And the third one is going to start at 4 seconds. So what you notice over here is the processing time that I have provided for each task is about 3 seconds, whereas these tasks arrive at an interval of about 2 seconds. So we need to identify how exactly those dependencies going to, or kind of whether there is going to be any kind of conflicts or something like that. I'm going to name it as task 2, and priority I'm going to set this to task 2 as well, which means my second task is going to have highest priority than the first one, whereas the third one is going to have highest priority with a priority of 3 over here. So in our case, or in VisualSim, hide the number, hide the priority. Okay, so what I'm going to do at this point is I'm going to bring in a plotter. I'm going to connect this to task plot of a system resource block or a CPU over here, and I'm going to run the model, try to understand how exactly it is going to see here. So when I looked at the activity graph for all these tasks what I have over here, I can see here this is my task 1, which is actually completing my 3 seconds of process execution time, whereas the second one is actually completing 3 seconds, and again the third one is actually taking 3 seconds of time. So we have actually selected a first come first serve basis scheduling algorithm over here. So what I'm going to do at this point is I'm going to make this to preemption over here. So I'm going to run the model again. So what I can see over here is the plot. The first task started at 0 seconds and it actually went all the way up to 2, at which I got a second task with a highest priority task of priority 2 over here. So which means I actually halted that first task or preempted the first task and taken the second task over here. And again, at 4 seconds, we got one more highest priority task, which is actually task 3, and task 2 got preempted, and task 3 got actually access to system resource over here. So as we don't have any kind of preemption for the third task, which is actually the highest one, it completes first and it takes the next highest priority task over here, and it takes the next highest priority task over here. So this way you actually have modeled over here kind of preemptive scheduling algorithm for the system architecture over here. In this case, it would be very simple scenario with only 3 flows here, but as system architectures goes complex with multiple application behaviors or access for different resources or memory related overheads and all that, the kind of problems that you could expect are much more than what we are seeing over here. Okay, so I'm going to make this scheduler type to round robin over here, and I have provided a round robin time slice of about, I'm going to set this to 1 here. I'm going to run the model. So what you see over here is we have actually provided a 1 second of time slot for each of these particular tasks, and they're executing on the target platform over here. So in addition to that, you can actually bring in other complex user-defined algorithms as well. So what I'm going to do at this point is I'm going to define this to fixed value 1, which means it is going to generate the traffic at different intervals right now. So what you see over here is the execution of the tasks itself over here with a round robin time slice or round robin approach of scheduling algorithm over here, in which I have multiple tasks that are being generated different times, and we are trying to understand which one is going to take a longer time period. So what you see over here is, so with a preemptive based approach over here, I can actually complete only task 3, whereas task 1 and task 2 are not able to complete because I'm actually running out of my simulation time over here. So I'll have to run for a longer time period. So this kind of analysis will actually enable you to make decisions on what is going to be the kind of timing or execution times that you can actually expect for execution of these tasks itself. And you can provide timing deadlines and make sure that the tasks are going to execute in the given timing deadline, and you can try to achieve those deadlines by either increasing the speed of the processor, or it could be the way how you have defined your memory hierarchy or memory subsystems and things like that as well. Okay, so this is a very simple model that we have actually looked at over here. And what we have done over here is we have defined a system resource using our CPU, or which actually helps me to define a CPU. And I have defined 3 different tasks that are starting at different timing intervals and provided a same set of execution time. And we were trying to understand what is going to be the impact of those task executions based on the type of scheduling algorithms that we are going to select. Okay, so any questions so far? Okay, so what I'm going to do at this point is I'm going to move over to a little bit complex system architecture in which we have a very detailed software behavior flow defined, and also we are going to keep the hardware architecture abstract again. Okay, so I'm going to delete all these blocks here. Let me go back to the slides. And in this case, what we are trying to do is we're actually going to model a kind of time and space partitioning, and we're going to consider a system with two partitions in which we have we're going to utilize a single core platform with two partitions, and we have provided a timing or period of about 20 millisecond time slot for each partitions, and we're going to run multiple tasks within that particular time slot itself and trying to see whether we are going to achieve the timing deadline or whether the tasks are going to exceed the timing deadline what we have allocated. So the major reason for doing this particular exercise is to kind of give you a feel of how quickly you can construct your software behavior flow and how you can consider the factors such as resource allocations or defining a complex scheduling algorithms, and to be able to model the workload scenarios and to be able to map your applications onto the target architecture itself. Okay, so what I'm going to do at this point is I have this digital simulator, and I'm going to change the stop time to about 100 milliseconds. I'm going to run this for about 100 milliseconds. And in addition to that, what I'm going to do is I'm going to bring in a parameter called number of partitions, because I can actually change these partitions and try to see what is going to be the impact of it. Okay, I'm going to set this to 2 as we have 2 partitions. And I need to consider a system resource. I'm going to bring in a system resource block, which actually helps me to model a processor or represent a processor block. Okay, and then what I need is I need to have a memory, as we are going to consider memory overhead related stuff as well. Okay, so if you notice here, we are actually considering the same resource blocks to model both processor and memory as well. Okay, and then what I'm going to do is I'm going to bring in a database block or a kind of lookup table, which actually helps me to define my different partitions and the time associated with each partition. So I'm going to delete all the stuff that I have in by default. I'm going to define a field called partition. Then I'm going to call or define a field called period. I'm going to call this partition as 1. I'm going to have about 20 milliseconds of time. I'm going to name it as partition. It could be anything. And I'm going to define the lookup field or input fields as partition. The reason is that it'll actually keep on looking at that particular row, and it'll enable me to get the period associated with that. I'm going to define this as here. So we have two partition tables over here. Two partitions over here with a dedicated or with a specific set of time period associated with that. So what we need at this point is we need a workload, or we need a traffic generator that actually helps me to define my different set of or different tasks that are associated with that. So what I'm going to do is I'm going to bring in a block called transaction sequence. I'm going to double click on this, and what I'm going to do is I'm going to define a series of fields here. I'm going to call this as task ID. And note that this can be an Excel spreadsheet that you can import from a import, and you can use it here. Okay, I'm gonna have a couple of other fields. For example, I'm gonna define what is the rate at which these different tasks are gonna get triggered, and I'm gonna define a couple of other parameters such as my semaphore, how many resources that I need to allocate for that. And in addition to that, I'm going to bring in such few parameters such as what is going to be my priority associated with that particular task, and the execution time. And then I can also bring in, or I can also incorporate deadline time as well, so that at the end of my simulation, I can always compare whether that particular task is actually meeting my deadline time or not. I need to incorporate one more as well, which is my task name, so that I can identify these tasks very easily. I'm going to call this as task 1, and this is going to run on partition 1, and this is going to generate at every 1 milliseconds, for example, and I'm going to need about 4 resources over here for a semaphore, and then I'm going to consider what is the priority associated with that, which is about 1, and I'm going to define the execution time of about 10 milliseconds. This could be anything. And the deadline time is about 12 milliseconds over here. So if you notice over here, the 12 milliseconds, I need to make sure this execution time is only for CPU executions, but it is not considering the memory access times, and you're going across the buses and all that. So those times would actually would be different, and that could vary based on the load across the buses and the memory availability as well. I'm going to copy and paste multiple times so that I have about 4 different tasks. I'm going to define or dedicated IDs, and I'm going to define this task partitions as 1, 2, and 1, 2. So as I have only 2 partitions, and I can define this at different rates I can mention. And I can also define a different set of parameters as well. Okay, I'm going to keep all rest of the things as is. Okay, so this will actually enable me to generate those different 4 different tasks. This could be a different scenario with hundreds of different tasks in your scenario as well. You can bring in those things by importing a Excel spreadsheet or things like that. Okay, so and then what I have over here is what I need to consider is how often or I need to trigger these blocks, or I mean how often I need to generate these different set of tasks. So that would be based on your major frame duration. For example, if I add up all my partition delays, in this case it's going to be about 30 milliseconds, and I can consider 30 milliseconds as my delay or major frame duration to trigger the tasks or generate those tasks itself. Okay, so this models my workload scenario itself. Okay, and now what I need is I need a block called a queue, which actually helps me to define my scheduler queue itself, or to be able to select a particular partition and send the transactions out or send the requests out to the target platform to make sure that you're not overloading a particular partition, or you're not kind of memory overflow related problems you're not coming across. So what this particular queue models your scheduler queue itself, and I'm going to call this as scheduler queue, and the queue will be actually based on, or this actually enable you to model multiple queues itself. In this case, as we have 2 partitions, I'm going to consider 2 partitions over here. Oops. One thing is that VisualSim, or you need to make sure that all the fields or values that you are entering are correct. So if you're not, it is going to give an error right up front. So you don't have to run the model or compile the model to check if there are something wrong or something like that. Okay, so I have defined my queue over here. So what I need over here, or what I need to model at this point, is I need to model a scheduling algorithm to make sure that the transactions that are sitting in my scheduler queue are sent out in a specific order, maybe based on the availability of my partitions, or maybe based on completion of a particular time slice or something like that itself. So to be able to do that, we actually provide two approaches. One thing is that using basic building blocks, using our if-else blocks or expression list or things like that, but also we provide more detailed script-based modeling approach as well. So what I'm going to do is I'm going to show you that how exactly it would look like. And here is actually, I'm going to bring in the same thing so that I can save some time. Oops, some overlap. So what I'm going to do is I'm going to encapsulate all these details in a hierarchical block so that I can keep it clean. Carry over. And what I'm going to do is I'm going to open up. And if you notice over here, the scheduler itself, we have modeled very in a very simple manner. So all we have over here is we have a trigger which actually mentions, or which actually tells us what time I need to trigger my task scheduler. In this case, we are actually triggering at 0 simulation time. By default, we consider the first partition, and we're going to send out the transactions from the scheduler queue over here. And then what we have here is we have a loop over here which actually helps me to pop out the next partition details, or the kind of or trigger the next partition itself after elapsing a particular time period. If you see over here, what we have here is a database block which is actually referring to my block what I have at the top, and it actually takes a field called period, which is actually based on, in this case, my partition 1 is actually having 20, or 2 is having 30 milliseconds, which means after elapsing 20 milliseconds, the next partition will actually get triggered, and that the transactions that are sitting in that particular partitions will actually send out. Okay, so I'm going to connect this over here. I'm going to make sure looking at the same thing. Copy and paste it. Okay, this looks good. Okay, so and then what we need here is that we have successfully modeled our scheduler, and also we have modeled our scheduler queue as well. So the other approach that actually we enable you to model a scheduler is based, or is with scripting language, in which you can actually model very complicated algorithms as well. In this case, what I'm going to show you over here is we have a scheduler over here, and we have the algorithm which is actually defined using our scripting language, which is actually 98% or 95% similar to a C language, in which you actually have you can model your while loop or if-else statements and things like that. If you see over here, we are actually waiting for a certain time period. Maybe it could be based on the slice time, what we have provided, and how many partitions I have in my system, and what is the time associated with each partitions itself, and which partition I need to trigger, I need to boot up, and things like that. So in this case, we have a round-robin based algorithm that we have defined. And in this model, we actually had about 7 different partitions, and each partition was actually provided with dedicated time periods. And the combination of all these partitions will actually provide us a major frame duration of about 16 milliseconds or something like that. So it will keep on going through all these different partitions, and it will send out the transactions that are tasks that are sitting in that particular partition itself. Okay, I'm not going to go over this at this point. So I actually showed you a script-based scheduling algorithm modeling approach, and also using our block algorithm based scheduling algorithm definitions. And what I need at this point is I need to have, or I need to do a kind of resource allocations to make sure that each tasks are provided with sufficient memory. So what I need at this point is I need to have a block called quantity resource allocations. So what we have over here is we have a block called resource allocation, and what I can provide is I can provide a maximum of about uh, eight resources. And in this case, we have, as we have two partitions, I'm going to have or define this as, maybe I can just define it as two. So what it does is I have two partitions, and this can actually model your memory related stuff as well, or it could be your scheduler, semaphore requirements you can model over here. And this particular block is associated with a resource queue or free block as well. So which means you have allocated some memory over here, but after execution on your target processor, once the task execution is over, you need to free up that particular allocated memory or allocate resources. So that we actually do it with this particular resource queue as free block. And this block requires a certain set of fields. For example, it requires the quantity request, which means what is the amount of resources that you're requesting, and then what is the priority associated with that, and also the dimension. So in this case, dimension is related to the partition itself. So as we have two partitions, we are going to trigger from which or to which partition you are actually requesting for resources or things like that. Okay, so to provide those, all those details are actually available as part of the transactions that I have defined over here. What I need to do is I need to just send those requests or fields in respective fields or ports itself. So what I'm going to do is I'm going to bring in a expression list block, and I'm going to delete all the stuff, and I'm going to define a new port called, for example, in this case, all I need is I need what is that? I need quantity request, which means my semaphore request in this case, and then I need the priority associated with that, and then what I need is I need partition. So which partition that you're actually triggering. Semaphore, and then what you have is input dot priority. In this case, it is actually task priority. So what I'm doing essentially over here is I'm actually just sending portions of these different data structure fields in a respective port itself. Okay, and partition is going to be based on input dot task partition. Okay, and I don't have any kind of conditions to send the data out. You can simply provide input dot input. Okay, so I'm just going to utilize this particular block to save some time. So what we have over here is I just have to connect these blocks to these corresponding ports. Okay, so what I have essentially over here is I have defined different ports, and all those different ports are connected to corresponding ports of my resource allocation block over here. And then what I need here is I need to perform a memory read operation. Right, so you have allocated the resources, system resources, and I need to do a memory read, and to do that I'm gonna define, or I need to map my incoming requests to a memory scheduler or a system resource at the top. I'm gonna call this task number as 5. Task priority is gonna be priority, and the time, it could be based on the type of the memory that you're selecting and things like that. But in this case, I'm going to just set this to 1 millisecond, but this could be completely different. You can actually consider the memory access times and the type of the memory and the clock speed at which you're running that particular memory itself, and all those stuff you can consider as well. Memory read operation. And then what I have, or what I need is I need to perform, once the data is available, I'm gonna do a task execution on my CPU. I'm gonna double click on this. I'm gonna define it as CPU. I'm gonna define this as task ID so that I will know which task is taking how much time. I'm gonna define this as task priority. So if I have highest priority tasks that are coming in, and if I have not completed it, I can actually preempt it and I can start executing. And then the time associated with that is execution time, which we have actually defined in the table. Okay. And then what I need is I need to perform, once my execution is over, I need to perform memory write operation. And for this, I can provide a different set of memory access times. Okay, so the way how these mapper blocks works is we actually look at the name here. So we actually do something like named mapping. So if the parent scheduler name is actually available in the model, the task will actually send over to that particular block in a virtual manner. So we don't really have to connect it by wires or something like that. Okay, so this will actually go to the memory block and it will see how long that particular task is going to execute, and it will wait for that particular time period. And also it will look at the type of the scheduling type that you have, if you have any kind of highest priority tasks that are coming in. If there are no, it will actually come back once it is finished and it will take the next one. So it will again go to the processor and it will spend that execution time what you have defined, and it will come back, and then you do your memory write operation. Okay, so once that is over, you're actually freeing up your allocation, memory allocations, and that completes your task executions. But what I can do at this point is I can capture the latency associated with that, and also I can trigger the next task next partition once my execution on that particular partition is over. Okay, so I'm gonna just delete it and mention as what is gonna be my next partition. So once the tasks on that particular partition is over, I'm gonna take up the next partition and start executing. Okay, I'm gonna just connect this over here. So this will take up the next partition and it will start executing. Okay, so to capture my latency information, all I need is I need to know what is my current timestamp and at what time that particular task has been generated. So which is actually we capture using input.time. By connecting a simple text plotter will actually provide us information on what is the end-to-end latency that I'm going to capture. Okay, I'm going to run the model that I have already assembled up over here, and in which I'm capturing my end-to-end latency. Also, I'm looking at utilization of my resources as well. So I have provided a resource of about 10. Out of 10, how many resources will be actually utilized during the course of a simulation or the lifespan of that particular application itself. Also, we are generating the statistics at the end of the simulation. I'm going to run the model, try to understand what exactly the simulation results would look like. And what I'm looking at over here is this particular plotter is actually providing me the task executions itself. For example, if you see over here at the bottom, this is the very first one is actually my task 1, which is again got preempted by a highest priority task again. And then after it finishes, the first task again uh, started processing, but it is not completing its execution time. But before completion of the execution time itself, we got one more highest priority task, and ultimately we can actually see that my first task is actually completing its simulation time at about 82 milliseconds, whereas it was actually supposed to finish at 10 milliseconds, but it is actually finishing at 82 milliseconds. So this is a kind of, this could be a real problem if the task is not actually having any kind of timing deadlines, right? So at the top, the blue one is actually capturing my memory related stuff. The values that are actually providing 5 is memory read operations, whereas uh, the blocks actually that are going up to 6 is actually memory write operations. So that are actually defined in the schedule or mapper blocks here. Task number, which is actually provided to 5, and the other one, which is actually provided to 6 over here. Okay, and in addition to that, very interesting factor that we need to consider is what is my end-to-end latency as well, because your task processing time may not be sufficient for your complete system performance. You may actually have to consider end-to-end latency as well. But if you see here, have captured my end-to-end latency time, have generated that traffic, and I have the delays associated with each task in my scheduler queue as well. And also I have additional delays associated with memory read operations or CPU processing and memory write operations and things like that. So I was actually able to complete with a maximum latency of about 56 milliseconds. That is actually kind of my maximum delay that I have captured over here. But if I look at my resource utilizations, which I've actually provided over here, I can see here my maximum quantity or resources utilized is about 4, but in most of the times I'm actually using only 2 resources out of 10 resources. So you don't really need to have, or you don't really need to provide so much allocations or resources to be able to have a successful system exploration over here. So this actually provided us information on what is going to be the kind of my memory requirements to be able to have a successful completion of my task processing. And also I'm going to try to understand my scheduling behavior itself. So which task is taking more time, and at what timestamp I'm going to complete that particular task processing. Also, I'm going to try to understand what is my end-to-end latency across my system platform itself. Okay, so a little bit complex system architecture compared to this one that we have here. I'm going to bring up that over here with a RAD 750 board, in which what you see here, the bottom portion is actually quite similar. I have my task generator, and I have my task queue itself, and I have my resource allocations, and I have my DMA read operations and task processing and write operations, and done. And at the top, we have the RAD 750 board, which is actually the library block that we offer with MPC 750 processor, which is actually again having external cache and memories and a DMA controller associated with that and all that. I'm gonna run this particular model, and over here the task table is actually having information on different tasks that I have and different or execution of these different tasks, execution on different partitions itself, and also the resources itself. It could be the semaphore, or it could be the timers, availability of the timers and things like that. So we have provided those details over here. And if I go ahead and run the model, so over here we are actually trying to capture the processor performance as well. So what is my MIPS, and what is my instantaneous and average power consumption in my system platform itself. It's going to take a little while to run the model, as we are using hardware accurate library blocks to model the entire hardware architecture, whereas the software behavior flow is exactly the same way how it was there earlier. And if you see here, my end-to-end latency capturing over here, I can see here these tasks are actually executing under the time deadline. So I'm not really taking more time. And looking at the MIPS here, I'm actually getting an MIPS maximum of about 140 million instructions per second. And I'm also looking at my average power consumption versus instantaneous power consumption as well. Right, so I have a maximum of MIPS of about 142, whereas minimum is about 87, whereas mean MIPS is about 106. Right, and also I can see that there are few tasks that are actually exceeding the timing deadline as well. Right, so we can capture more information about which task is actually exceeding the timing deadline and why it is exceeding as well. So in this case we are not capturing, but you can capture those details as well. Okay, so this is one model with a detailed software behavior flow, which includes your traffic generator or task generator, which includes your scheduler queue and the scheduling algorithm and allocation of the resources and memory read and write operations and mapping to the processor itself. But if you see over here, the processor is actually taking the synthetic instructions that are actually generated for a set of tasks that are going to run on the target platform. So when we say synthetic instructions, those actually mimic the real applications load on the real hardware architecture itself, which includes varieties of different mnemonics details and the delays associated or cycle delays associated with each partitions or each instructions as well. I'm going to show you that in a little bit to give you a feel about how exactly that file would look like. And here I have that instruction table, so in which you actually define all your different group of instructions associated with the selected processor that you're going to utilize. And here we have all the mnemonics associated with that. And at the bottom we have a task table with a set of names and the number of instructions associated with each task itself. And the way how we get this particular number is very simple. And also this is very much accurate in terms of a real system itself. For example, if you have about 100 lines of assembly core, C core, you would actually have about, you can multiply each line with about 5 or 6 and you can actually capture the total number of instructions associated with that particular task itself. So that is a kind of pretty good accurate number in terms of total number of instructions associated with each task. And on the right hand side we have define out of 6,000 instructions, our arithmetic type would be about 53%, whereas the multiplication, divisions and all those stuff would be about 20%. And there are going to be about 1% of branch instructions and 5% of load store instruction, things like that. So these are more of assumptions that we have done here. If you have pretty good information about your application software, then you can actually come up with a very good numbers over here. But in addition to this, we also provide you our capability to bring in the real trace files that you have generated from your system itself, from your system that you have with you. You can actually plug in your real trace files into VisualSim and you can map those instructions into the target platform and get very accurate performance reports as well. Okay. So I'm going to bring in a different system model over here in which I have a statistical processor model, whereas I have a hardware accurate bus and a hardware accurate DRAM block over here, whereas I have modeled my different interfaces that are having, for example, in this case I have Arink 825 and AFDX traffics that are coming in. Also I have modeled my scheduler over here, which includes my algorithm and scheduler queue and the virtual machine details. For example, what are the different partitions that I have and the time associated with each partitions as well. And the simulation time, again, we are trying to understand which are the tasks that are actually exceeding the timing deadline, which are the tasks that are completing within the given timing deadline over here. So which is pretty much same and just different versions of the model that I was actually going through. Okay, so let me know if you have any questions. I can go back and I can answer those questions at this timestamp. Okay, so other model that I wanted to stress today is ability to model, or our library block, which we actually provide for modeling the RTOS itself. So far you have actually seen a ability to model your applications as a sequence of tasks and all that. We are actually providing a block called RTOS itself, which actually embed all these definitions that are actually embedded inside this particular block. And this particular block actually references the lookup table that I have defined at the right-hand side over here. So what I have here is, if I double-click on this RTOS block, I can select the operating system vendor, and I can select the target processor and how many cores I have in my processor itself. In this case, I've selected a RAD 750 and it is having only one core of processor. And I can provide what is going to be my major frame duration, combining all my different partitions and all that. And also I have defined other overhead delays such as task setup delays or preemption delay and partition delays and all those stuff. And these tables that I have on the right-hand side here, for example, this one, is actually enable me to define my different set of tasks and what is the rate at which each tasks are getting generated and the memories associated with that and execution time and task priorities, as I mentioned earlier. And also you can define your dependencies between those tasks as well. For example, you can wait for a particular message coming from a different task itself. Okay. And in addition to that, here we have the partition details. I can define what are the different tasks that are going to execute on my each partitions. Okay, and you can define a different set of messages that are going to generate from different tasks. In this case, if you notice over here, when I mention break one, what it means is as soon as I actually complete this particular break one, I'm going to actually generate a message called M1, which is actually related to a kind of a body task. And sorry, so as soon as I actually complete my body task, it is actually going to trigger my break task. So this is something like you're modeling your precedence over here, or kind of dependencies in your system or task definitions itself. Okay. Also, you can define your interrupts and timers and event generations to be able to capture or to be able to define multiple tasks in the model itself. So if I go ahead and run the model for this, so what we are looking at over here is we're actually looking at what are the different messages that are sent out and what are the different tasks. Maybe I'll slow down this. I'm going to animate this or model so that my simulation will actually slow down. What you can see over here is you're actually looking at what time that major frame is actually set up, what time a particular task is actually getting started, and what is the state of that particular task itself. If you see over here, starting at 0.011, it is actually getting completed at 0.013 over here. So in between, it was actually reading and it was performing write operations and it was executing on the target processor and things like that. All right. And also we are looking at what are the different messages that are being generated by different dependent tasks as well. Okay. So these are more of statistics that we capture. Okay. So one of the factors that I have to mention over here is when I enable this debug message, debug animation execution, what you see over here is a kind of highlighting of each blocks when I actually goes through the simulation. For example, if you see here, we're actually performing a DMA operation, which is DMA read operation, and after that you perform your execution, and then you actually perform DMA write operation. So it actually clearly provides you a kind of execution flow and trying to enable you to debug your system model in a better manner as well. And also if you introduce any errors into the model, for example, let us say you've forgotten to actually incorporate a parenthesis or something like that. So if you actually run the model, it'll actually highlight that particular line. So if you see here, you're actually missing a parenthesis. So you don't really have to compile or anything. It'll actually immediately shows that particular error and the name of that particular block, which is actually associated with that as well. So debugging with VisualSim is actually very simple, and most of the blocks are actually enable you to fix those problems as soon as you actually edit those as well. For example, if you miss a colon over here, you can't really actually make any kind of commits and all those stuff. Okay. So today we actually looked at the factors such as how can I define my software behavior flow, and how can I model those scheduling algorithms using a simple using simple building blocks or kind of block algorithm based approach, and also script based approach. And also we looked at how can I allocate resources for my system resources, or maybe my software resources. And also we looked at how can I map my software applications onto the target platform. And also we looked at how can I model multiple partitions in my system, and how can I run those run tasks on multiple partitions and make sure that the tasks are executing in the timing deadline or not. And also we looked at various different analysis as well. For example, looking at my software resource requirements, how much software resources I need to have, or it would be the total end-to-end delay itself or latency itself, or it could be the task processing time, how much time each task is taking based on the type of algorithm that you're selecting as well. Okay, so this concludes this today's training session, and if you have any questions, please post in your questions. And also as you go along your practice session, or when you actually practice these tutorials, if you come across any questions, please send us an email to the email ID provided over here, or you can also provide or send an email to info@mirabilis Design as well. So we will actually help you understand those concepts as well.